I want to know how many of you regularly teach algebra classes, abstract algebra classes? 2. Okay, fine. So this talk is mainly meant at people who don't regularly do it. Okay. So what I want to talk about is a topic in group theory. So this is about abelian groups. So in a course on group theory, generally the course or abstract algebra, the part on group theory generally ends with the fundamental theorem, structure theorem for finitely generated abelian groups or finite abelian groups, something of this kind. That is the highlight of this course and of the group theory part, and so that is what I am going to concentrate on. So but before I begin, the initial part, at least for the first few minutes, I am not going to restrict myself to abelian groups of any particular kind, but abelian groups in general. Now, so as Sundar mentioned in his talk, sometimes when students come for interviews, we ask them questions like, are these two groups isomorphic or are they the same? And typically they are not able to answer. Unless they have already seen it before, they are not able to answer the question. So let me start with examples of abelian groups. So let's begin with some simple examples of abelian groups. So the simplest of course are the cyclic groups. And cyclic groups, they come two kinds. One is the infinite cyclic group, which is Z itself, or you have the finite cyclic groups, quotients of Z, Z or Zn. By Zn I mean Z mod nz. So these are the cyclic groups, and these exhaust all the cyclic groups. Now both Z and Z mod nz, if you also know that Z mod nz is actually a ring, it has a multiplication, and when we are regarding it as a group, we are just forgetting the multiplication. In general, you take any ring, you can just forget about the multiplication and regard it as a group, the additive group of that ring. So just like we did it for Z or Z mod nz, we can take additive groups of other rings. So additive groups of rings or fields So I am going to give examples. Let's just take Q for example. That's a ring. You can consider Q as an abelian group, or say R. Any ring you can take and consider it as a group under addition. And if further the ring is a commutative ring, then you can consider the group of its units. In particular, if it's a field, you can consider all non-zero elements there, and that will form a group under multiplication, that will form an abelian group under multiplication. So the next example is multiplicative groups. I won't say rings here, I'll just say fields, because rings, it may or may not, the multiplicative group may not be commutative. I'm only interested in abelian groups. So multiplicative groups of fields, say, or the group of units of commutative rings in general. So this, for example, say Q star, non-zero rational numbers under multiplication, non-zero real numbers under multiplication, or non-zero complex numbers under multiplication. These are also examples of abelian groups. And then when you already have some examples of abelian groups, you can consider some subgroups, and they could conceivably be different. So subgroups of these. Such as, for example, if you consider the real numbers under multiplication, the non-zero real numbers under multiplication, you could just restrict attention to the positive real numbers. Of course, that's closed under inversion and closed under multiplication. So that forms a group R plus, positive real numbers under multiplication. So we have one small collection of groups here, abelian groups. And the kind of questions that students should be asked, and or they should think for themselves is, are these different, are they the same, are they all different, actually different groups? So one question we should ask is, are all of these different? Of course we have to qualify, quantify, we have to say what different means. As sets, of course, they are all different, but different means different as groups, that is, are they non-isomorphic as groups, i.e. So this kind of question is the question that our student should try to answer. So how do we know whether things are isomorphic or non-isomorphic as groups? So if you want to show that things are not isomorphic, then what you do is you try to find a property that one satisfies, a property, a group theoretic property that depends only on its group structure, that one satisfies and that the other does not satisfy. Then these two cannot be isomorphic as groups. So there are many such properties. So the first thing is to note that an isomorphism of groups means, by definition, it's a bijection which is also a group homomorphism. It must be bijective and it must be a group homomorphism. So if two things are not in bijection with each other, then certainly they cannot be isomorphic as groups. So that itself will separate many of these. So for example, so the first thing is, so to distinguish groups, we can consider, for example, cardinality. So number of elements in that group. The cardinalities are different, of course you cannot have groups to be isomorphic. So this is countable, this is countable, these are finite and each one has a different number of elements. As n varies, each of these zns has a different number of elements, finite with different cardinalities, infinite countable, and the rest, these are all uncountable, right? So already we have distinguished between this, well, this and this, we'll come to that in a second, but we distinguish between these at least, and these are uncountable, so these cannot be either this or those. So we have already distinguished so many of them just based on cardinality. But that's not a group theoretic property, right? That's even more basic than group theory is set theory. Just by set theory you have distinguished these things. Even as sets they cannot be the same, so certainly they cannot be the same as groups. Okay, so the next property that one might think of, which is an actual group theoretic property, is, and this is important for what we are going to do further, is whether that group is a finitely generated group. So next property I'll list is finite generation. So let me go into this a little bit more. What does finite generation mean for an abelian group? So if G is an abelian group, then it is finitely generated. I'll just say Fg. It is finitely generated if there exists a finite set of elements G1 to Gn in G such that each element of G is expressible as n1 G1 plus n2 G2 with the ni's belonging to Z. Okay, so here for the group abelian groups, it is normal to use additive notation. So we don't describe the group operation as multiplication, but rather as addition, right? when you use addition, it's always reserved for abelian groups. Multiplication can be either for an abelian group or for a non-abelian group. Typically for abelian groups we will use addition. And what does n1 g1 mean? n1 g1 means if n1 is positive, then it means you take g1, n1 copies of g1 and add them all together. If n1 is negative, then it means you take minus n1 copies of minus g1, which is the negative inverse of g1, add them all together. So this has a very specific meaning in any abelian group. Given what g1 up to jn are, the expression n1 g1 plus n2 g2 plus nk gk with the ni's and z has a specific meaning, has a specific element of that group. And if every element of g is expressible in this form, so nothing about uniqueness, nothing about no other condition. If you can express, if there are a finite set of elements such that every element of g can be expressed as this sum, then we say that the group is a finitely generated group. So it is important when one gives a definition to give examples both of groups that are finitely generated and of groups that are not finitely generated. So any definition you have to give examples of both things, something that satisfies the definition, something that does not satisfy the definition. Okay, so if you look at these examples, first notice that if the group is finite, then of course it is finitely generated. So if G is finite, then clearly it is also finitely generated. That's no problem. You can take all elements of G together, that itself is a finite set. Every element of G can of course be written in this form. You can take one of the ones to be 1, all the rest to be 0, right? So finite groups are finitely generated, but there are others. For example, Z, that's not a finite group, but Z is finitely generated. In fact, cyclic groups are generated by just one element. By definition, that's what cyclic group means. Cyclic groups are singly generated, so certainly they are finitely generated. So cyclic groups are finitely generated, though they may not be finite. Z is a finitely generated group, not finite. Okay, then we come to these. What about these? What about these groups? Now one important fact about a finitely generated group that follows immediately from its definition is that finitely generated groups are always countable. Not the converse, right? I am just saying finitely generated groups are countable. Why is that? Because finite generation can be expressed another way. See, it's clearly if you G1 up to Gk are fixed and you are only varying the N1 up to Nk, N1 up to Nk each is varies over Z. So Z cross Z cross Z cross Z, how many ever k's are there? That many Z to the k. So it's clear that maps onto G, that set maps onto G. Since it maps onto G and that is a countable set, the product of Z with itself any number of times, finite number of times is countable. So this is also going to be, G will also be a countable thing. So finitely generated groups are always countable. So that rules out all of these. So all of these are not countable. So these are not finitely generated. But what about Q now? So that leaves Q now. We have this we know is finitely generated. This is not finitely generated. Q here, that's countable, right? So this condition doesn't rule it out. So now I claim that Q is not finitely generated. We want to say Q is not a finitely generated abelian group. What does it mean to say not? That's, as Sundar was saying, it's very important to know what not means. Not finitely generated means no matter which finite set of elements in Q I take, you cannot express an arbitrary element of Q as a Z linear combination of this chosen finitely many. So to prove this, take any finite set of elements of Q and say that set is P1 by Q1, P2 by Q2, Pk by Qk. So here is a set of k elements in Q. I want to show that no matter which I take, it will not be possible to generate Q. An arbitrary rational number cannot be written as a Z linear combination of these. So to show that an arbitrary one cannot be written, all I need to do is to produce one which cannot be written as a Z linear combination of these. So take some prime P that does not divide any of Q1 up to Qk. Right? So take any prime number which doesn't divide any of those. We know that that's possible. There are an infinite number of primes. Only finitely many divide this, only finitely many divide this, only finitely many divide this, and there are totally only finitely many of those. So of those infinitely many primes, pick one which doesn't divide any of the Q1 up to Qk. So now I claim that if you look at 1 by P, 1 by P is not expressible as N1 P1 by Q1 plus N2 P2 by Q2 plus Nk Pk by Qk. For any N1 up to Nk in Z. That's my claim. I want to say you cannot write 1 by P in terms of this, and that's easy to see, because if 1 by P was equal to that, for if 1 by P is N1 P1 by Q1 plus Nk Pk by Qk, multiply both sides by Q1 up to Qk, by the product of Q1 up to Qk to conclude. So what do you conclude? If you multiply by Q1 up to Qk, this side, each term, if I multiply this by the product of Q1 up to Qk, one Q1 will cancel, and then I'll have all the denominators will cancel in each one of these. So finally I'll be left with an integer on this side, whereas on this side I'll have Q1 Qk by P is an integer. Right? N1 up to Nk's are integers, so this thing, it follows that this is an integer. But we chose a prime which doesn't divide Q1, which doesn't divide Q2, which doesn't divide Qk, so obviously the prime cannot divide the product. That's a basic property of a prime. So this is a contradiction, right? So we have seen that no matter which finite set of elements in Q you take, it cannot generate. So Q is not a finitely generated group. It is countable but not finitely generated. So the converse of this is false. Q is an example to show that it's false. So that distinguishes between Q and Z, of course. Okay. So now we still have the rest to distinguish from. Okay. So two criteria I wrote down here. One is cardinality, another is finite generation. So here let me write down my third criterion. Third criterion, this is a much easier criterion actually than finite generation, and it is to consider elements of finite order. See, if two groups are isomorphic and one had an element of order 10, then the other one also will have an element of order 10. That's a group theoretic property. So you could just see, how are there elements of finite order? We could begin with the question, are there elements of finite order? So look at this. So let's look at say R, right? Look at the group of real numbers under addition. Are there elements of finite order in R? Under addition, if you take a real number and keep adding it to itself any number of times, will you ever get to 0? No, you won't. So R has no elements of finite order. So this has no elements of finite order. Let us consider R star, right? R star is the group of real numbers, non-zero real numbers under multiplication. Now, are there elements of finite order in this group? Yes. minus 1 is, right? If you take minus 1 times minus 1 is the identity 1. So minus 1's order in that group is 2. So this has, it has an element of order 2. So that of course distinguishes these two groups. So R and R star can therefore not be isomorphic because this has an element of order 2, that has no element of order 2. Okay. Now what about R plus? Positive real numbers under multiplication. Now are there elements of finite order? If I take a positive real number and keep raising it to any power, I will never get 1 unless I started with 1. If it is bigger than 1, keeps on becoming bigger. If it is smaller than 1, keeps on going towards 0. You will never get 1 unless you started at 1 itself. So this also has no elements of finite order. Okay, so that did not help, but that is okay, maybe there are other criteria, let us see. What about Q star? Rational numbers under multiplication, non-zero rational numbers under, same reason, right, minus 1 again. So this also has an element of order 2. But anyway, we distinguished this already because this is countable and that is not. We already distinguished Q star. Anyway, let me just mention that. What about the complex number stars? C star, non-zero complex numbers under multiplication. Again same reason, it has elements of order 2, it has elements of order 3, it has elements of order 4, it has elements of every possible order, right. So this has, the roots of unity are all finite order, so has elements of all orders. Okay. So I guess we have distinguished most of them, right. This has no element of order except 2. R star has no, you cannot have a cube of something to be 1, right, unless it is 1 itself, right. So here there are no elements of order 3, this has elements of order 3, so this is not the same as this. So what only remains to be distinguished is R and R plus, everything else we have sort of separated, they cannot be isomorphic. So how do we distinguish? So can we distinguish R and R plus? Are they the same group? One is real positive real numbers under multiplication, the other is real numbers under addition. So are they the same group or are they different? And then of course we can just refer to Sundar's lecture and say the exponential function gives you a map, right? The exponential function, so these are the same, they cannot be distinguished. So these are the same. So consider the map, exponential map from R to the positive real numbers, x goes to e to the x. We know it's a bijection, right? Everything has a natural logarithm, all positive numbers have a natural log, and that will be some element of R. So this is a bijection from here to here, and further exponential function satisfies the property that e to the x plus y is e to the x times e to the y. That just says that mapping is a homomorphism. So this is a homomorphism which is bijective, therefore this is an isomorphism of groups. This is the kind of reasoning that we would like our students to understand, appreciate, and hopefully get it themselves, right? That is what we want. We want them to think in this manner. We want them to think when you're given a question like, are these two groups the same or not? So we would like them to think about how do we distinguish, what kind of group theoretic properties might help distinguishing between one and the other. Okay, so this is so much about general abelian groups. Now let me move on to what I really want to talk about, and that is finitely generated abelian groups. So first I guess I should explain why I am concentrating on that theory. Okay. The reason I am concentrating on finitely generated abelian groups is very simple. If it is not finitely generated, the theory is too difficult. General abelian groups can be quite peculiar and quite hard to analyze, whereas for finitely generated abelian groups there is a very nice structure theory, as we all know, and there is a very beautiful theorem. It is the first important classification theorem in algebra that our students meet. It is this theorem. So it is important to understand this as well as possible and communicate it to them. So, but before I get into finitely generated abelian groups, let me get back to our list of examples. So we had a small list of examples of abelian groups, and we would like to enlarge the class of abelian groups. One easy way of enlarging is to build new groups from old, and the easiest way of building new groups from old is the cross product construction. So recall that if H and K are any two groups, then H cross K, the Cartesian product, also gets a group structure by doing pointwise operations. That is H1 K1 times H2 K2 is H1 H2 times H1 H2 comma K1 K2. So this is a way of cheaply getting new groups from old. So you just take any two groups that you already knew, take their cross product, you will get another one, a new one. This way we can start with our small collection, leaving out all the non-finitely generated ones. We essentially have only the cyclic groups, right? We only have, if you on that whole list, if you consider the things which are only finitely generated, the only things that remained on that list were the cyclic groups. So we start with the cyclic groups and then do this cross product construction. In if H and K are abelian, then by notation, then H cross K is sometimes also denoted by H direct sum K. This is just a different notation. H cross K or H direct sum K mean the same thing when H and K are abelian groups, and that other notation is meaningless if H and K are not abelian groups, right? This direct sum notation is used only exclusively for abelian groups, and it means the same thing as H cross K. Okay, so we can start with our small collection, which is the cyclic groups, and take direct sums. So to get new examples, of finitely generated abelian groups, so begin with the cyclic groups, two kinds, the finite one and the infinite one. Begin with the cyclic groups and take direct sums, or what's the same, products. So begin with some small collection of cyclic groups, maybe Z, Z2 and Z3, and take the direct sum, for example. So that is a new group that you have created. Now, the amazing thing about finitely generated abelian groups, and that's what the structure theorem says, is that this process completely exhausts the class of finitely generated abelian groups. That means every finitely generated abelian group is of this kind. It is a direct sum of cyclic groups. So the fundamental theorem says that every finitely generated abelian group is isomorphic to a direct sum of cyclic groups. This is part of the theorem, and if you think about it, it's a really very amazing theorem. What did we start with? We just started with some group. We imposed the condition that it be an abelian group. Then we imposed the condition that there is some finite set of elements in it such that every element in that group is a Z linear combination of these elements. That's all we said. And then from that we are going to conclude that necessarily that group must be of this kind. It's a direct sum of certain copies of Z, certain copies of finite cyclic groups. Essentially that is the only possibility. So it's quite a remarkable theorem. Okay, this is part of the theorem I said. This is the existence part. That is, every finite group is isomorphic to a direct sum of cyclic groups, but can it be expressed as a sum of cyclic groups in essentially different ways? That is the next question we need to answer further. The decomposition further the decomposition, I'll state it a bit vaguely, is unique up to reordering the factors. That means if I express an abelian group as a sum of cyclic groups in two different ways, then the only possible way that they could differ is that I could write the same group as Z directum Z3 directum Z2. That's obviously the same group, but that's the only thing I can do. I can only rearrange the factors. I cannot essentially write it in a different way by writing it as okay. Did I? Sorry. Yeah. No, up to isomorphism you can. I'll come to that in a second. I made a mistake here. So is a direct sum of cyclic groups. Okay, let me say a little more. This is not correct. This is wrong. This is not a fundamental theorem. This is a fundamental error, right? Okay, it is not true that it is unique up to reordering the factors. For example, here is this group Z direct sum Z2 direct sum Z3. Now we know from abelian group that Z2 direct sum Z3 is isomorphic to Z6. So this group is also the same as Z direct sum Z6. Now that looks fundamentally different. It's not just a rearrangement of this, right? So this statement is not true. What is true is the following. Further, the decomposition is unique up to reordering the factors provided each of the cyclic groups has prime power order. Here this doesn't have prime power order. That's a problem. 6 doesn't have prime power order, right? If each one of those things has prime power order, then this decomposition is unique. Now the uniqueness theorem is a little bit subtle. I know that when I studied abelian groups, I distinctly remember I had lots of problems trying to understand this uniqueness of decomposition. This is not a simple matter. You need to pay close attention to what is really happening and what statement is being asserted here. That's why again I made a mistake. Even when I am saying this, I made a mistake. It is unique only if you assume that these are of prime power order. There is another kind of uniqueness. I will discuss that later. Okay, now let me get back to your question.
I don't agree with that statement.
Which statement?
Z plus or minus the circle Z2 the circle Z3 is isomorphic to Z plus circle Z6.
You don't agree with this statement?
Because the first one is isomorphic to Z cross Z2 cross Z3.
Yes.
Which has points of 3 coordinates.
Yes.
And the second one has points of 2 coordinates.
Correct.
How can they be isomorphic?
They can be I am not saying they are identical. Okay, so let me show you. Let me remove the Z first. I am claiming that those two are isomorphic first. You don't agree to that either, right? You don't agree that Z2 direction Z3 and Z6 are isomorphic, do you?
As integers they may be same, but when you treat them as points with two coordinates,
Yes.
how can they be?
How can they be means we just have to get back to definition of isomorphism. So let us see why they are isomorphic. It's extremely important to understand this point. So claim Z2 direction Z3 is isomorphic to Z6 as groups. That is my claim. Okay, so I'll prove this claim. So if I want to prove this claim, your objection is they are not the same set. I agree, they are not the same set. I am not saying they are the same set. To show that they are isomorphic, I have to give you a homomorphism from one to the other, and that homomorphism should be 1 to 1 and it should be on to, right? That's all I need to do.
Preserves the structure.
Which preserves structure, yeah. It's a homomorphism means preserves structure, and it must be bijective 1 to 1 and on to, which I will do. So proof. So let's first define a map. First define a map phi from Z to Z2 direction Z3. I'll first define a map from here to there, right? What is the map? Phi of A or phi of n equals, I have to give you one element of Z2, one element of Z3. I'll just take n bar, comma n bar. So n bar means the coset of n in Z2. This n bar means the coset of n in Z3. So this is a map from Z into Z2 direction Z3. No problem, right? There is a map. That there is no problem. Okay. Now I claim that this phi is actually a homomorphism. That means what? Phi of m plus n equals phi m plus phi n. That's what I want to show. That also is true. Phi of m plus n means what? M plus n bar, m plus n bar. But what does m plus n bar mean? How do you define addition in Z2? The way addition is defined in Z2 is m plus n bar is m bar plus n bar. That is how you define it. So this is m bar plus n bar. Similarly in Z3 also this is m bar plus n bar. That is how you define addition. And how do you define addition in a direct sum? I said you define it component wise, right? So this is the same as m bar plus n bar. Component wise, this and this, they are the same. But this one is phi m, that is phi n. By definition again, phi m plus phi n. So I have defined a homomorphism from Z6 into Z2 direction Z3. Now I claim that this is not just a homomorphism, that this is a surjection. This is surjective. So next, phi is surjective. Now this is the hard part of the proof actually. To prove that phi is surjective is the really hard part of the proof, and this is called the Chinese remainder theorem. What was discussed in the algebra yesterday? Was that discussed? Chinese remainder. So Chinese remainder theorem says that phi is surjective. So I have a surjective homomorphism from here to there. Okay, let me not. So this is by the Chinese remainder theorem. Another way of seeing it, in this case it's easy to see, because if I take say the element 3 here, 3 goes to 1 comma 0, right? 3 goes to 3 bar is the same as 1 bar, and 3 bar here is the same as 0 bar. So 3 goes to 1 bar 0 bar, whereas say 4 goes to 0 bar 1 bar. So 1 bar 0 bar and 0 bar 1 bar are both here. So you can get any PQ by taking an appropriate combination. So in this case it's easy to see that this is surjective. Phi is surjective. Further, kernel of phi, what is kernel of phi? Is by definition all n in Z such that n bar equals 0 bar 0 bar. What does that mean? N bar is 0 bar in Z2 means n is divisible by 2. N bar is 0 bar in Z3 means n is divisible by 3. N is divisible by both 2 and 3. They are co-prime, so n is divisible by 6. This is the same as 6. Any multiple of 6 will go to 0 and only multiples of 6 will go to 0. So kernel is just 6Z. Therefore, by the whatever first isomorphism theorem, if you have a homomorphism, surjective homomorphism of groups and that is the kernel, then this modulo the kernel is isomorphic to this. So by the first isomorphism theorem, Z mod 6Z is isomorphic to Z2 direct sum Z3. That's what we set out to prove. That is what I said. Z6 is isomorphic to Z2 direct sum Z. It is not the same as sets. It may have, this may have 14 coordinates, that may have only 2 coordinates. That is not relevant to this issue. Isomorphism just means you should have a one-to-one and on-to mapping from this group to that group, which preserves the group operations, which this does. So these two are isomorphic. Okay, so coming back to this one. So I want to discuss finitely generated abelian groups, and the reason for discussing finitely generated abelian groups is exactly this beautiful theorem, that every finitely generated abelian group is only a sum of cyclic subgroups. You start with the simplest building blocks there are, which are the cyclic groups, and you do the simplest possible way of combining them, which is taking direct sums, and then you get everything. That's all. So let's see how this theorem is going to be proved. Yes, so let me remark once again, this theorem has two parts. The first is an existence part, that is everything is a sum of cyclic groups, that's one, and the second is a uniqueness part, that is if you write it as a sum of cyclic groups of prime power order, then the only any two such rearrangements differ by only permutations. Okay, so in order to prove the fundamental theorem, there are many approaches. So I have prepared two different approaches.
Can you explain that uniqueness part?
Yeah, so the uniqueness part says, see, first you express it as a direct sum of cyclic groups, right? In one way and then in another way. Suppose you can. For example, this can be expressed as Z, Z2, Z3 or Z, Z3, Z2. That you can do. You can always rearrange, but it says that you cannot do it in another way where everything has prime power order. Here everything has prime power order, here everything has prime order. Z2, Z3 have prime order, leave out Z's of course. Right? This is infinite, but these have prime order. If you can express it in some other way as a direct sum of groups with prime power order, then that way can only be a rearrangement of this. You cannot do any fundamentally new way. That's what it says. It is just, this uniqueness is exactly similar to the uniqueness in prime decomposition of a number. So if you want to decompose 72, it is 3 squared times 2 cubed, that is 3 into 3 into 2 into 2 into 2. If you want some other way of writing 72 as a product of primes, the only thing you can do is to rearrange the factors. You cannot do anything else. Exactly similar, this is saying. Exactly similar. But there it's primes, here it is prime powers. There's a small difference, but basically that's it. Okay, so in understanding this fundamental theorem, the main role is played by the so-called finitely generated free abelian groups. So that is what I'll start with next. That's a big name but easy concept. A lot of the work in this theorem goes into understanding what the finitely generated free abelian groups are. So let me define it. Definition. As I said, it's an easy concept. The groups 0, Z, Z direct sum Z, Z direction, Z direction, Z, and so on are called. So I'll abbreviate this by finitely generated free abelian groups, FG, FAGs, right? So just those groups, that's all. There's one for every non-negative integer. There's Z, Z direction Z, Z direction Z direction Z, 4 copies of Z, 5 copies of Z. How many other copies of Z? 0 copies of Z means is just the 0 group, 1 copy of Z is just Z, 2 copies of Z is Z direction Z. All these groups are called finitely generated free abelian groups. So first notice that they are indeed finitely generated, right? A direct sum of cyclic groups is always, a finite direct sum of cyclic groups is always finitely generated. This, for example, is generated by 3 elements, 1 0 0, 0 1 0, 0 0 1. Any element there can be expressed as a Z linear combination of these 3 elements, right? So these are finitely generated and these are called free abelian groups for a reason we will get to in a second. Okay. So as I said, these are finitely generated and they have something called a standard basis. So these groups have I'll put it within quotes, standard basis. Standard basis is E1, which is 1 0 0 0 0, E2 0 1 0 0 0 up to ER 0 0 1 for the group ZR. ZR means the direct sum of R copies of Z with itself, right? So this ZR has this standard basis. Standard basis, I am not defined what standard basis. I am just saying I will call these elements E0, E1, E2 up to ER as a standard basis of Z. The important property that it has is that every element here can be expressed as a linear combination of these. That is certainly true. If I take a column vector K1, K2 up to KR, it's the same as K1 times E1, K2 times E2 up to KR times ER, all added together. So it can be expressed in terms of those, but more importantly, every element can be expressed uniquely in terms of those. Here, for finitely generated free abelian groups, there is a notion of uniqueness of decomposition, and which is the key thing. So the standard basis satisfies the following property. Note that any element of ZR can be expressed uniquely as K1 E1 plus K2 E2 plus KR ER with K1 up to KR in Z. It can be expressed and can be expressed in only one way. And as I said, the way you do that is, for example, this element is an arbitrary element of ZR and you can write it only this way as K1 times E1 plus KR times ER. Okay, so this is a property that these groups have, that is, they have a subset of elements within them. In this case, the subset is the subset E1, E2 up to ER, an R element subset. They have an R element subset such that every element of that group can be uniquely expressed as a Z linear combination of that subset. So now I will define what is a basis. This concept of a basis is a collection G1 up to Gn of elements of G such that any G in G is uniquely expressible as n1g1 plus k1g1 plus kngn for ki's in Z. So very slight difference from what is a generating set. So we said a set of elements generates G if every element of G can be expressed this way. It's a basis of G if every element of G is uniquely expressible as. If there's only one way you can write it, then it's said to be a basis. Now not all abelian groups have basis, certainly not. Right? For example, if you take the group Z2, right? I want to show what elements does it have. It only has 0 and 1, right? And 1 alone by itself is not a basis because the element 0 can be expressed as 0 times 1, it can also be expressed as 2 times 1, it can also be expressed as 4 times 1, any even number times 1 is 0, right? So there is no unique expression, so there is no basis. That's the only possible thing, it could be a basis and it's not, right? So not all abelian groups have basis, but we see that these groups do have basis. This is a basis. In fact, the standard basis is a basis in the sense of that definition. However, free abelian groups, let me say finitely generated, right? I am only going to be worried about finitely generated, even if I forget to mention. Finitely generated free abelian groups have a basis, namely the standard basis. Okay, now, but one must not think that that is the only basis that they have, right? The standard basis is certainly a very important and useful basis for dealing with these groups ZRs, right? It's a useful and important basis, but that is by no means the only basis. So let's just look at the case of R equals 2. So the standard basis is not the only basis. Say consider Z2. Okay, Z2 is vectors, column vectors, 2 size column vectors, entries in Z, right? So let's consider Z2. We know that 1 0 0 1 is a basis, right? This is a basis. This set E1 and E2 is a basis. Now if you think about it a little bit, pictorially what is Z2? Z2 consists of all points in the coordinate plane whose both coordinates are integers. So this is the origin, then Z2 consists of all these points. So this I will mark as origin. All those integer lattice points, all points both of whose coordinates are integral. Now in this I could consider, for example, let's see. I had a particular thing in mind. So consider F1 is 2 1 and F2 is 3 2. Let us consider these 2 points, right? 2 1, where is 2 1? 2 1, it's this, and 3 2. It's that 2 1 and 3 2. I claim that this is also a basis. So my claim is claim the set F1 F2 is a basis for Z2. So what do we have to do in order to prove this? So what does it mean to say that it's a basis? I have to show you two things. I have to show you that every element of Z2 can be represented as a Z linear combination of F1 and F2, 1, and this representation is unique, 2. So let me first do uniqueness. So I'll first do uniqueness, then I'll do existence. Okay, so suppose I take some element of Z2 which has two different expressions in terms of F1 and F2. So suppose AF1 plus BF2 is also equal to CF1 plus DF2. I would like to conclude that A and C are equal and B and D are equal. I.e., I can write this as A minus C times F1 plus B minus D times F2 is 0. And write out what this means, which implies A minus C times the vector 2, 1 plus B minus D times the vector 3, 2 is 0. 0 means the 0 vector, the 0 element of that group, right? So A minus C times 2, 1 plus B minus D times 3, 2 is 0, 0. But this is just, I can write this as the equation if I do the matrix 2, 1, 3, 2 times the column A minus C, B minus D, I'll get A minus C times 2 here plus 3B minus D here, that is the first component here, and A minus C times 1, B minus D times 2, that is the second component, equals 0, 0. But you see that this matrix is an invertible matrix, right? The determinant is 4 minus 3, determinant is 1. So if the invertible matrix times some vector is 0, then that vector has to be 0, right? By invertibility, A minus C equals 0 equals B minus D. That's what we wanted to show for uniqueness. So this is the uniqueness part. Now existence part. See, if I want to show you that everything is a linear combination, it's enough to show that E1 and E2 can be expressed as a linear combination of F1 and F2. Once I know that E1 and E2 can be expressed as a linear combination, I already know that everything is a linear combination of E1 and E2, so then I can obviously write everything as a combination of F1 and F2. So existence suffices to see that E1, E2 are linear combinations of F1, F2. Now let's see what that means. So what does it mean to say E1 and E2 are linear combinations? So I want A, B, C, D and Z such that, so let us say E1 is AF1 plus BF2 and E2 is CF1 plus DF2. This is what I want. I want to show that E1 and E2 are Z linear combinations of F1 and F2. Then of course everything will be Z linear combinations. Again, if I write this out as an equation, this says that how shall I say this? So let me write this way. So 1, 0 equals A F1 plus B F2 and 0, 1 is C F1 plus D F2. So this becomes equivalent to one matrix equation 2 1 3 2 A times 2 1 plus B times 3 2 C D. So I get this equation. Those things that I've written down over there are exactly equivalent to this, right? A times 2 1 plus B times 3 2 is 1 0, and C times 2 1 plus D times 3 2 is 0 1. So you get this matrix. So all I'm trying to say is I can find A B C D which satisfies this equation, but look at this. What is it saying? This says something times this unknown matrix is the identity matrix. So all I'm saying is that this is invertible. Invertible where? Invertible over Z. I must find elements of Z here which satisfy this condition. Now that is, we can invert this. 2 3 1 2 times 2 2 check that this is correct, right? This is obviously correct, right? I just inverted this matrix. The determinant of this matrix, notice, is 1. So I do not have 1 by AD minus BC is not needed. I just have to invert A and D and change the signs of B and C to get the inverse. Right. So therefore we have proved, thus F1 F2 is a basis. The idea of the proof should be clear. Actually, it is far better to work out one example than to do the proof in all gory detail and not get anything across. I am sure with this one example worked out, anybody can work out the proof in general. If I give you any matrix, an invertible matrix over Z, then the columns, so let me claim the following. Similarly, if A is any R cross R invertible matrix over Z, that means its determinant is plus or minus 1, i.e. determinant of A is plus or minus 1, then the columns of A are a basis of ZR. So here is a matrix, its columns, this is an invertible matrix over Z, its columns are F1 and F2, they are a basis of Z2. In general, if you have same proof will work even in the R by R case. There is nothing special about 2 by 2 I used. This is word for word you can do this proof in general. Okay. So basis is not unique. However, one thing happens to be unique. That basis also had 2 elements, this basis also has 2 elements. You had E1 and E2 and F1 and F2. So one should ask, now is that as true? Is that always true? If I have sorry, before I get to that question, let me give you another definition, then we will get there. So here is a lemma, very easy to prove. If an abelian group G has a basis G1 up to Gn, then G is isomorphic to Zn. I am saying the only groups that have basis are exactly what I told you earlier, which is the finitely generated free abelian groups. They are the only ones which have a basis, finite basis. If you have a finite basis of n elements, then G is necessarily isomorphic to Zn. And this is very easy to prove. Why? Because take any element. I have to give you a homomorphism from here to here, which is an isomorphism. Take any element of G, right? Write it in terms of the basis. So I will get K1 G1 plus K2 G2 plus Kn Gn. So I get therefore K1 up to Kn. I send the element of G to K1 up to Kn. easy to check that this is a homomorphism, that this is injective, surjective, all of them will be very trivial to check just from the definition of what a basis means, right. So in other words, the importance of this lemma is it's giving you an alternative definition for finitely generated free abelian group. When I began, I said a finitely generated free abelian group are exactly the Zns. Now I am saying that if an abelian group has a finite basis, that is exactly the same thing as a finitely generated free abelian group. So if I want to show that something is free, for example, I need not actually show that it's isomorphic to Zn. All I have to do is to produce a basis, and then it will be isomorphic to a Zn necessarily. Okay, now let us come to this number of elements in a basis. While we see that the basis is not unique, we can ask, is the number of elements in a basis unique? So in other words, we could ask the following question: could Zr and Zs be isomorphic if R is not equal to S? Right? And now we did so many techniques for trying to see whether groups are isomorphic or not isomorphic. None of the techniques work. So what was the first technique? First technique was cardinality. Both are countable, so that doesn't do anything. Second one was finite generation. Both are finitely generated, so that also doesn't work. Third technique was, we said look at elements of finite order in this side and that side. That also doesn't work. There are no elements of finite order except the identity here, no elements of finite order except the identity there. So these three things that we discussed don't help in distinguishing these two groups. So we must do something a little cleverer to be able to distinguish these two groups. Okay, so yeah, so how do you distinguish these two? I claim they are not isomorphic. Why? Huh? But we have not proved, we do not know that the number of elements in a basis will be the same. Maybe I will have one basis of 2 elements, another basis of 3 elements. We haven't ruled that out yet. So this does need some thought, right? So we do need to spend some time thinking about why these two are isomorphic or why these two are not isomorphic. So let me give you an indication of how this is done. And this anyway introduces another important concept in abelian groups. So let G be any abelian group. And n be any element of Z. Then we define Ng to be the set of all Ngs such that as G varies over see, I am using additive notation for abelian groups, so I am writing this as n times G. If I were using multiplicative notation, I would write this as G power n. So just take a group, abelian group, and take the nth power of every element there and take this collection. This collection will also form a group because it is an abelian group, so G power n, H power n is the same as GH power n, right. So the product of two nth powers will also be an nth power, so you will get, and the inverse also of an nth power is an nth power, so you get a new group, subgroup of G, and that is called Ng. If you are using additive notation, it will be called Ng. If you are using multiplicative notation, this will be called G to the power n. Whatever it is, it is a subgroup of G. And what is important about this subgroup is the following statement: if phi from G to H is any homomorphism, then phi of Ng will be contained in NH. An nth power of an element will always go to an nth power, right? X, if x is y power n, then phi of x is phi y power n, right? So an nth power will always go to an nth power. That's all I am saying. It's simple but important. So Ng goes to Nh. So now let us try come back to this thing and see. Okay, under a homomorphism I said Ng goes to Nh, but what if phi were an isomorphism? If phi were an isomorphism, if phi from G to H is an isomorphism, then phi of Ng must be equal to Nh. Because you could take, for example, the inverse isomorphism and then Nh will come back into Ng by the inverse, right? Or just directly you can show using 1-to-1 and onto that phi of Ng is equal to Nh. So now suppose these are isomorphic. Suppose Z to the R and Z to the S are isomorphic. Suppose phi going from Z to the R to Z to the S is an isomorphism. And let me take n to be 2, say, take n equals 2. And phi will map 2z to the R into 2z to the S. So here I have a subgroup here and here I have a subgroup there. This is an isomorphism. It takes this subgroup to that subgroup. Now if I have an isomorphism and I have G1 H1 and G2 H2, I have an isomorphism from G1 to G2 which takes H1 to H2, then the quotients will also be isomorphic. This is an abelian group, so everything is a normal subgroup. So I claim that then Z to the R mod 2Z to the R will be isomorphic to Z to the S mod 2Z to the S. Now let me try to analyze what exactly is Z to the R mod 2Z to the R. Claim Z to the R mod 2Z to the R is isomorphic to Z mod 2Z to the power R. So I am writing power R here, whenever I write power R I just mean a direct sum of R copies of that, right? Z to the R means Z direct sum Z direct sum Z R copies. Z mod 2Z to the R means Z mod 2Z direct sum Z mod 2Z direct sum Z mod 2Z R times. Power R just means R copies direct sum together. So I want to claim that Z to the R mod 2Z to the R is isomorphic. How in general does one prove an isomorphism statements of groups? What is the technique that we have? If you want to show that two things are isomorphic, what do you do? Particularly when one thing is a quotient.
You define one homomorphism from the numerator.
Top. So first, that's all you have to do. You have to define a homomorphism from the numerator here into here, which should be surjective homomorphism, and then you should show that the kernel of that homomorphism is exactly this. Then the first isomorphism theorem will tell us that this quotient group is isomorphic to the image, which because it's surjective is the whole thing. So define, and generally it will be easy to do that. So define theta from the numerator into Z mod 2Z power R. What can it be? Theta of K1, K2, Kr equals, I mean I write it as column vectors normally, but here I have written it as a row, it does not matter. So theta of K1, K2 up to Kr is, I have to give you R elements in Z mod 2. Obvious thing is to take bars of each one of these. This K1 bar, K2 bar, Kr bar. That's it, that is theta, and it's clear that theta is a homomorphism. So easy to see, theta is a homomorphism and is surjective. If I take any ones and zeros here, I can take the same number ones and zeros here, and obviously it goes there, right? So theta is a surjective homomorphism. And what is the kernel? So kernel of theta consists of all z1 up to zr such that k1 up to kr such that k1 bar, k2 bar, kr bar equals 0, 0, 0, 0. That's the identity element. That just means k1 should be a multiple of 2, k2 should be a multiple of 2, kr should be a multiple of 2, which is the set of all k1 up to kr such that 2 divides each ki. But then what does that mean? If 2 divides each ki, which is the set of all k1 up to kr such that k1 up to kr is 2 times something, k tilde 1, k tilde r. That's exactly, 2 divides each one means I can factor out the 2 and write it as 2 times something, and on the other hand if I can write it as 2 times something, then obviously 2 divides each one. This is all k1 up to kr, which is twice something else, but that is the same as 2 zr. 2 zr also consists exactly of those elements which are twice the elements of zr. So the kernel is this, and so we have finished the proof of the claim, right? So what? So what now? So coming back to this question, if there were an isomorphism from here to here, it would take this subgroup into this subgroup, hence it would also give you an isomorphism from this quotient group into that quotient group. But this quotient group is z mod 2z to the power r, that is what we have said there. This quotient group is z mod 2s to the 2z power s. How many elements are there in this one? In z mod 2z power r, so no, 2 power r only. Why r plus 1? 0 1, no, it's just 0 1 power r. So each coordinate can be 0 or 1, 0 or 1, 0 or 1, 0 or 1. Each has 2 choices and there are r places, so 2 power r. It's just 2 power r. This is 2 power r. This cardinality is 2 power r. That cardinality is 2 power s. So if they have to be isomorphic, then r has to be equal to s. So therefore we have proved this. Could these two be isomorphic if r and not equal to s? No. Once we have proved this, now we can define that what it means, what the rank of a free abelian group is. So the rank of a finitely generated free abelian group is the number of elements in any basis of it. And how do we know that any two bases have the same number of elements? Suppose I have a group G and I have one basis with 5 elements and another basis with 10 elements. I already know that if I have a basis with 5 elements, then G is isomorphic to Z5. I also know if it has a basis of 10 elements, G is isomorphic to Z10. But Z5 and Z10 we just showed are not isomorphic. So that means both the bases must have the same number of elements. Therefore any two bases have the same number of elements, and that number is called the rank. Thus the rank of Z2 is just 2. Rank of Z3 is 3, so on and so forth. Okay. But the important thing to note is you cannot make this definition unless you have already proved this statement. Without proving this definition is meaningless, because the rank could be 2. If it had a basis of 2, it had a basis of 3 also, then the rank could be both 2 and 3. So rank won't be well defined. So to make this well defined, you must have answered that question earlier. Okay. So I am going very slowly actually, it does not matter. See, I might only get, see, the most important thing in this fundamental theorem of finite abelian groups is understanding these free ones, is understanding z to the r's. If you understand that well enough, then the other things will follow somewhat easily. So I will spend lot of time on this, even if I do not actually get to the theorem, it is okay. Okay, so invariance of rank, that is what we have done. So now let's now discuss why are these so important. So I am saying that most of the work is here. So why is it that these groups, which seem very special, right, you are just taking a sum, direct sum of copies of z, a few copies, 2 copies or 3 copies or how many ever copies. Why are these groups so special? Why do they deserve to be studied carefully? And the reason is fairly simple. So why are finitely generated free abelian groups important? Why are they important? For the study of finitely generated abelian groups. The reason is any finitely generated abelian group is a quotient of one of these. So proposition or lemma, any finitely generated abelian group is a quotient of some Zn. Zn's are the finitely generated free abelian groups. So everything is a quotient of Zn. So you must think of this as a kind of analog to Cayley's theorem. So Cayley's theorem says if you have a finite group, it is always a subgroup of Sn, and that somehow identifies Sn's as important. They are important because every finite group is a subgroup of Sn. So if you are studying Sn, then essentially you are studying all finite groups. This is also one such thing, but this is for quotients. Now this is saying any finitely generated abelian group is a quotient of some Zn. So if you study the Zn's well, then essentially you are studying all finitely generated abelian groups, because everything is a quotient of some Zn. If you study this well enough, then you will be able to say something about all finitely generated abelian groups. And this is much easier to prove, as it turns out, than even Cayley's theorem. Cayley's theorem itself is not hard, but this is very trivial proof. What does it mean? I want to show it is a quotient of some Zn. What do I know? I just have finitely generated abelian group. Means what? I have a set of generators for it. So let G1 up to Gn be a set of generators for G. Let G1 up to Gn generate G. What does it mean to say that it generates G? It generates G means that there is a every element of G is expressible as K1 G1 plus K2 G2 plus Kn Gn. So each element of G is of the form, not necessarily uniquely, K1 G1 plus K2 G2 plus Kn Gn. Now using this, I want to get a surjective homomorphism from some Zn into G. So which n will I pick? Obviously I should pick the same n as this n, right? If it is generated by 3 elements, I should pick Z3. If it is generated by 15 elements, I should pick Z15. So the same n I will take. So define phi going from Zn to G by, I have to tell you where a typical element of Zn, which is a tuple K1 K2 up to Kn, where does it go? By theta of K1 K2 up to Kn. I mean, where could I send it? Look at this. Obviously I should send it to K1 G1 plus K2 G2 plus Kn Gn. The main point is this is a homomorphism, right? Not difficult point, easy only, but that is the point. So this is a homomorphism. And this uses the fact that G is a abelian group, right? If G were not abelian, then this thing would not be a homomorphism in general. but for an abelian group this is always a homomorphism. So we have a homomorphism from Zn to G, and obviously phi is surjective. Why is it surjective? That's what it means. That's what it means for G1 to Gn to generate G. We just said every element of G can be expressed in this form. That means every element of G can be expressed as theta of something. That means theta is surjective. It's just a translation of the notions, nothing, we are not saying anything. So I've got a surjective homomorphism from Zn to G. That means G is isomorphic to a quotient of Zn by the kernel. If I take first isomorphism theorem says G is a quotient of Zn. Thus G is a quotient of Zn. Okay. Right. Fine. So now we know that every abelian group can be expressed as a quotient of Zn. So now let us try to see what is the next thing. If you want to study an arbitrary abelian group, once we know that this is a quotient of Zn, we should study what the kernel is, of course. Then we will know something about what the quotient group is. If you know what the kernel of that homomorphism is, then we will know what that group G is. So that means we are led naturally to study subgroups of Zn, right? Now we want to study the kernel, which is a subgroup of Zn. So we would like to know something about subgroups of Zn. See, the whole proof goes in a very natural fashion. You go from one to the other in step by step. There is a reason for each of these steps. So I am trying to explain, that's what I am trying to explain actually. You are all familiar with the proof, no doubt, but one has to convey this to the students, that why we are doing this. You can read a proof and then present it, but often it is hard to say why it is being done in one particular way or why it is being done in another particular way. Finally, of course, there is no why. You cannot answer all the whys. Finally, it just is. It's just that works. That's the final answer. But nevertheless, to a good extent, you can explain roughly why we are doing the things we are doing. So we can now try and explain. See, one of the theorems that you will study when you are doing finitely generated free abelian groups is that a subgroup is also free. So one might ask, why should we study this? And the reason why you should study this is obvious now. See, everything is a quotient of Zn. So if you know something about the subgroups, then you will also be able to say that is, you will know something about the kernel, then you will be able to say something about G. So a natural reason is to be able to say something about G. So let me state the proposition. This is a nice proposition. If okay, any subgroup of Zn is isomorphic, or let's say Zr, any subgroup of Zr is isomorphic to Zs for some S between 0 and R. Every subgroup of any Z dar is always isomorphic to a Zs. I am not saying it is actually a Zs, it is isomorphic to Zs, right. This is not very trivial to prove, it needs something. So it needs, this is a proof by induction on R. So proof, this is by induction on R. Right. So first suppose R is 1. If R is 1, then we are considering subgroups of Z. And what are the subgroups of Z? Z is a group under addition. What are the subgroups of Z? The subgroups are NZ. And the proof of that depends on what? One word or two words. Why are the only subgroups of Z NZ? Which one? The proof that the only subgroups of Z are NZ depends on what? no, no. How will you prove that the only subgroups of Z are NZ? How do you know there is nothing else? NZs are certainly subgroups, I agree. How do you know that is all? Why is there no other subgroup? Yeah, so this is a question that one has to think about, right? Why is that? NZs are obvious subgroups of Z. That it's easy to check that they are all subgroups, but why are they the only subgroups? Why is it that nothing else is a subgroup of Z? So let's do that first. So suppose that K, yes? Any idea of the two words?
Generated by 1.
Which one?
Set of
Z is generated by 1, but how do you know that any subgroup is of that kind? How do you know that maybe the subgroup may not be a cyclic group? How do I know that it's always going to be cyclic? It needs proof. So suppose that K is a subgroup. Okay? Now if K is just 0, if K has only 0 in it, that's a subgroup, that's fine. That is just 0 Z. Let's leave that out. Assume that K is not 0. K is not the subgroup which consists only of 0.
subsets which are generated by any element of the zero subgroups.
Yeah, that's true, but how do you know that there is, that is all? How do you know that there is not a subgroup which is generated by 7 and 852? That's generated by two elements of Z.
Subsets which are generated by any integer
Yes?
is any z.
That I agree. No, you're not getting my question. I agree that those are subgroups. I am asking why is there no other subgroup? We have to prove the other way. You have to prove the other way. I am saying I agree that those are subgroups, but why is it that nothing else is a subgroup? Why? That's my question. And that is what this proposition is dealing with. It says that every subgroup of Z to the R is isomorphic to Z to the S. For R equals 1, it says every subgroup of Z is isomorphic to Z to the S, where S is between 0 and 1. That means it's either the 0 subgroup or it is cyclic. Every subgroup of Z is either 0 or cyclic itself. That means it's generated by a single element. It cannot be generated by 2 or more elements. Okay, so assume that K is not the 0 subgroup. So among all elements of K, I can find, certainly there will be positives and negatives, because K is a subgroup. If it has a negative element, its negative also will be there. So it will definitely have some positive element, right? So K must have some positive integer. Right? It's not the 0 subgroup, so it must have some positive integer, because it cannot have only negatives, because the negative of a negative is positive. So it has some positive integer. Among all the positive integers in K, let us pick the smallest one, right? So pick the smallest and call it D. That we have to show serves the purpose. So pick the smallest and call it D. Now I claim that K is actually dz. And therefore I will have proved that K is of the kind you are saying. It's a multiple of Z by something. So I want to prove that K equals dz. So what is the key point in seeing this?
That D is the smallest
Hmm.
possible. So we'll take any element in that
K.
K,
Hmm.
write it as some multiple of D and
That's so the answer I am looking for is division algorithm. The whole proof of this is only two words, that is division. If I say division algorithm, the whole proof is essentially done. So let's complete it. The key point is only the division algorithm. So K equals dz. So since D belongs to K, certainly dz is in K. That is clear. If D is an element of K, then I can 2D, 3D, 4D and minus 2D, minus 3D, minus 5, everything will be in K. So dz belongs to K. Now take any element of K any A in K, divide by D and write it as A equals QD plus R, where R lies strictly between 0 and D. R can be 0 but strictly less than D. Now look at this, A belongs to K, we know that, D belongs to K, so A minus QD also belongs to K. That means R has to belong to K, but R is smaller than D and D was the smallest positive element of K, so that means R cannot be positive, which means R must be 0. So by choice of D, R is 0, hence A belongs to dz. So I took an arbitrary element here and showed that it belonged there. So this is the proof that the only subgroups of Z are either the 0 subgroup or cyclic subgroups, which are of the form nz for n in Z. So that does the basis case for this proposition. This whole proof is the basis case, R equals 1 case for this proposition. So now let us do the inductive step. So we now assume that we have proved it for R up to something, up to K we have proved it. So suppose that for R less than or equal to K minus 1, any subgroup of ZR is free of smaller rank. That's what it's saying. Assume we have proved that for R less than K up to K minus 1, any subgroup of ZR is necessarily isomorphic to a free group of smaller rank. Suppose we have proved this. Now take a subgroup K of ZR. We will consider two cases. So what is ZR? ZR consists of all tuples, R tuples of elements of Z. So case 1. If the subgroup K is contained in this group 0, K1, in the set of all, let us consider the following subgroup of ZR, all elements whose first coordinate is 0, right? That you agree is a subgroup of ZR, right? The inverse of something whose first coordinate is 0 is also first coordinate 0, the sum of something whose first coordinate is 0 is also 0. So this is a subgroup of ZR, and what is this subgroup isomorphic to? The subgroup of ZR of all elements whose first coordinate is 0 is isomorphic to what group? Is isomorphic to ZR minus 1. Obviously these are R minus 1 things, all belong to Z, and the addition everything respects is just like ZR minus 1. So this is isomorphic to ZR minus 1. So if K is contained here, then K would be isomorphic to a subgroup of ZR minus 1, but we have already proved for smaller ones that this will be free, right? So we may assume that this case doesn't arise. If K is contained in this, then no, I'm not, sorry, I didn't quite say. Suppose that for R less than or equal to K minus 1, so now I have to start with ZK, sorry. I fumbled with the notation. Okay. Now take a subgroup K of, we have proved it for up to K minus 1. This is isomorphic to Z K minus 1. So if this is isomorphic to a subgroup of Z K minus 1, then we are done. So then K is contained in Zk minus 1, so done by induction. That's case 1. That means if K has all elements whose first component is 0 only, then we are already done by induction. So assume that that's not the case, case 2. Else consider the first components of all elements of K. Right? We know that it's not just 0, it's not only 0. There are some elements in K whose first components are non-zero. So let's consider the set of the first components of all elements of K. I claim that this is a subgroup of Z. This forms a non-zero subgroup of Z. Why? Because if I take two, suppose this is the first component, that is the first component, this is the first component of this element, this is the first component of this element. When I add these two, the sum will be a first component of some other element, or the sum of those two elements. The difference will be a first component of the difference of those two elements. So it's very clear that the first components of all elements of K forms a subgroup of Z, and it's non-zero because we are not in this first case. That's the first case is the case where it's all 0. We are in the second case where it's non-zero. So it is of the form nz for some non-zero n. So the set of all first components of elements of K is exactly the subgroup nz of Z, which means there must be some element in K whose first component is n, right? So there is, because the set of all first components is of the form nz, so there must be some element in K whose first component is n. So some element of K has first component n. So let's call that F1, which is n and then something something something. This belongs to K. Yes, okay. So now what I do is so now consider L, which is a set of all things in K whose first component is 0. Right? Take the set L of everything in K whose first component is 0. This is a subgroup. So this is a subgroup. This is a subgroup of just this part, that is Z to the K minus 1. Hence by induction is free with less than or equal to K minus 1 generators. That is the inductive assumption. So L, which is all elements of K whose first component is 0, is actually a free abelian group with at most K minus 1 generators. Now my claim is K, I claim, is isomorphic to L direct sum all multiples, the group generated by that single element, whatever, n star 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 star. This is F1, that's what I called this F1, right? What did I, yeah, F1. So I claim that K is isomorphic to L direct sum, the group generated by F1. Then I am finished, because this is actually z to the power something, that something is less than or equal to k minus 1. Together I add one more z, this is obviously isomorphic to z, it's a cyclic group and it cannot have, it's not, it cannot, you can, no multiple of this thing is ever going to become 0. So this group is actually isomorphic to z, and then I have z to the power something less than or equal to k minus 1. So together I will have something z to the power something less than or equal to k. That is what I want to prove, provided I prove this claim. I want to prove that k is isomorphic to this subgroup direct sum that subgroup. So how do you know when I have an abelian group, I have two subgroups given, I want to know when it is a direct sum of these two. Now this is typically done much earlier, and one shows that when is G isomorphic to H cross K, you need that H intersect K must be trivial and HK must be the whole of G. This is all you need. Well, if you are dealing with the non-abelian groups, you also need H and K to be normal. In this case you do not need that. All you need to see is that the intersection of these two is empty, one, just the 0 element, and you need to know that every element of K can be expressed as an element in L together with an element here. So let us see that. So proof, take any element of K, say some A1, A2, AK. What do you know about A1? What do we know about A1? A1 is the first component of some element of K, but we know that the set of first components of elements in K forms the subgroup NZ. So every first component of everything in K is always a multiple of N. So all we can conclude from this that this A1 is a multiple of N. So we know A1 equals N times something P. Now what do we do? What we do is we take this A1 up to AK and subtract P times F1 from it. So consider A1 AK minus P times F1, which is N something something. And what happens? A1 is N times P, so the first component will become 0, then I will have some things. What can we say about this element? What we can say about this element is the following. It certainly belongs to K because this element belongs to K. We took an element belonging to K, and this element also belongs to K because that is how we chose, F1 belongs to K. So this minus P times this whole element belongs to K. So this element belongs to K and it has first component 0. But the elements in K which have first component 0 is exactly L. So therefore this belongs to L. So we have shown that an arbitrary element of K can be expressed as a multiple of this together with summed with an element of L. That is what I am trying to show here. An arbitrary element of K can be expressed as a multiple of F1 plus some element of L. That is one part. The other part is I have to show that L intersect this is empty. That is obvious. If I take any multiple of this except the 0 multiple, in the first component I will have something non-zero. It's N times something non-zero will still give me something non-zero. If this is non-zero, then how can it belong to L? L consists of all those things whose first component is 0. So the intersection of these two is just the 0 element. So we have proved. Therefore we have proved K is this. So I didn't write out, let me not write out the proof. So let me just say complete. I just said it, but I didn't write it. So therefore we conclude that a subgroup of a free abelian group is free abelian with smaller rank. But you should not take this to mean that the only subgroups, if I take Z3, it does not mean the only subgroups of Z3 are that Z direct sum Z, Z direct sum Z direct sum Z. There are peculiar subgroups, there are subgroups which sit inside Z3 in an odd way, but nevertheless they are isomorphic to only either 0 or to Z or to Z square or to Z cubed itself. And here there is an important difference between these group case and vector space, finite dimensional, and the dimension of V is equal to the dimension of W, then V equals W. Once you know that the dimensions are equal, necessarily V and W are equal for finite dimensional vector spaces. This does not happen for groups. However, if H contained in G are free abelian groups, finitely generated free abelian groups. Finitely generated is the equivalent of finite dimensional vector space. Are finitely generated free abelian groups, and the rank of G is the rank of H. It need not be that G equals H. Why? Because we just saw Z contains 2Z. 2Z is also isomorphic to Z. So the rank of 2Z is also 1. Rank of Z is also 1. And 2Z is contained in Z. Both are of rank 1. But they are not equal to each other. This cannot happen for vector spaces. If you have the one dimensional vector space contained in a one dimensional vector space, they have to be equal. But this is an important difference between groups and vector spaces. That is because of the structure of that Z. Okay. Subgroups. Yes. So we have completed the proof of a result which says a subgroup of a free abelian group, finitely generated free abelian group, is also finitely generated with a smaller number of generators. If you take a subgroup of Z10, it has to be Z10, Z9, Z8, Z7, it has to be isomorphic to up to 0. This has an extremely important corollary which is not at all obvious. If without doing all this theory I just stated this corollary right at the beginning, then it would be extremely hard to see how one would prove such a result, and this is the very interesting corollary. So if G is an abelian group generated by G1 up to Gn, and H is a subgroup of G, then H is also finitely generated with at most n generators. This is a very beautiful and very remarkable result. See, it is remarkable for the following reason. This result could have been stated right at the beginning. As soon as I told you what finite generation means, what number of generators, all these things once one knows, I can state this result. I can state if G is an abelian group and it has n generators, then any subgroup of G will have a fewer number of generators, can always be finitely generated with fewer number of generators. Now this might seem very plausible, yeah, it seems likely, but how does one prove it? It's not easy to prove. It's not easy to prove without having gone through all of this. It's a corollary of the result we have just said. So let me prove this, and let me remark that, again another remark, this is false for non-abelian groups. There are non-abelian groups which are generated by only two elements, and it has subgroups which are not finitely generated at all. You cannot generate that subgroup by any finite number of elements. For non-abelian groups this could very well happen, but abelian groups we are in the nice case. So let us see how one proves this result. And again this is related to the reason I said that finitely generated free abelian groups are important. They are important because everything is a quotient. All finitely generated groups are quotients of these. So here is the proof of corollary. What do we know? We know that G is generated by G1 up to Gn. Now if you translate this, what does this mean? This means that the group Z to the n maps onto G. So we know there is a surjective homomorphism phi from Z to the n to G. And what is this homomorphism? It's the one that takes E1 to G1, E2 to G2, En to Gn. So we have a surjective homomorphism. Now what do you have? You have H is a subgroup of G. So H is contained in G. Here is a subgroup. What we can do is, we can consider the inverse image of H under this homomorphism. So consider K. By K, it is not the kernel of this thing. I am considering K equals the set of all x in Zn such that phi x belongs to H. The inverse image of H, the inverse image of a subgroup will always be another subgroup. So I have K. K is a subgroup here, and since this mapping is surjective, this mapping will also be surjective. Why is this surjective? Because if I take any element in H, it belongs to G, so there is some element here, and that of course that element belongs to K, because K consists of all those such that phi of x is in H. So this is surjective. So we have K maps surjectively to H. But now we use the fact that we know something about subgroups. This is a free abelian group of rank n. So K is also a free abelian group of rank at most n. So by what we just proved, K is isomorphic to Zm for some m less than or equal to n. What does that mean? If this is isomorphic to Zm, I could take the images of E1 up to Em in H, they will generate H, because this is a surjective map. E1 up to Em generate here, and so their images will generate there. So that means H will be generated by at most m elements, where m is smaller than or equal to n, and that's what I have asserted there. Hence H is generated by m elements. So it's very crucial here that we knew this for free abelian groups. Free abelian groups, a subgroup of a free abelian group is itself free abelian with a smaller number of generators. Without that, we had no hope of just starting with an arbitrary abelian group G and an arbitrary subgroup H. There is no way of manufacturing something in H which will generate it. This is quite a tricky proof. The statement is very simple, but the proof is quite involved. It involves all of these things. Okay, so that is the corollary, and okay, so I've not, I've barely done, I think, I've barely done half of what I prepared. So sorry I didn't get to the main theorem, but nevertheless I think I've covered. Oh yeah, there's one more thing to cover. Even in free abelian groups, there's one more proposition to cover. But other than that, given these propositions, the fundamental theorem requires a little more effort, but not very much more. The important things is about free abelian group, because these are the things that when you do modules, these are exactly the same kind of arguments which will occur over and over again. These things are important. Z modules are the same as abelian groups, but you could consider other modules over rings, and many of these have generalizations or they are false for some interesting reasons. Okay, so I'll stop here. Thanks.